Hello, this is my first recording with sound. I would like to introduce you to my framework that I've written to simplify the process to interact with OpenGL. This is the most simple example that I could come up with. It basically just renders a triangle on screen. It looks like this. A triangle, each vertex a different color. Very basic. And this is all code that's necessary to run it. I mean, there's also the default setup, but it's just a function that does some setup, creates an OpenGL context, creates a window. Then here's a little bit of SDL code that handles events, nothing particular to my framework. And here OpenGL command to clear the screen. And here's the interesting part where I have a macro call that generates all the OpenGL commands that I need. In the beginning there's the triangle mode, or the primitive mode set to triangles, the amount of vertices set to 3. Here's a block of attributes. I have two attributes called aVertex and aColor. aVertex is filled with the data vertices. I initialized vertices here. This construct until here is simply an array, and the array buffer command outside of it transforms the array into an array buffer from OpenGL. So it copies the data onto the GPU side of the computer, but it keeps its type information intact. So the program knows that this data is from the type vec4f and not just flat data. And then when I pass vertices to the attributes, this information is used from the macro to generate all the code that's necessary so that I can use the identifier aVertex in the vertex main. As you can see here, aVertex is used and it works, and aVertex is just set to GL position. Very important, these are not predefined names. I could use any name. Just to give you an example, when I don't want to use the name aVertex, for example, I want to use aVertex XY, and I execute it, I will get error messages. On the right side, it's a bit broken because the colors don't work, but basically it tells me undefined variable aVertex, because now it's called aVertex underscore XY. It means if I also call this xy, it should work again. So when I want to use more attributes, I already have prepared something that's more data. It's not particularly useful, but just to show that I can use more data, I just add more data to my struct, and then I can use more data. Here I just add more data to the color, to the red-green space. And as you can see, I have now more color, or brighter color. Also not particularly useful, but you get the idea. And then I can also increase or add local variables as uniforms. For example, here I use the time, I use the timer. The timer is an object I created here. It's a stopwatch that starts running as soon as I start the program. And then I ask for the time, and then I convert it to a 32-bit float. That's stored in time, and then I can use time in both the vertex shader as well as the fragment shader. For example, I can add the GL position. I can add the time to the position, and then I have a moving triangle. And last but not least, I also use it in the fragment shader. For example, the color, I say color .air r plus equals sinus time mal forgot semicolons. Yeah, as you can see, the color of the triangle shifts. That's it for this example. Hello again. Here a small addition that I forgot to mention about the hello triangle example. I have a construct that's called debug result that helps to identify what OpenGL code is actually generated. I just have to write debug result in the top of my macro call. Then when I execute it, everything happens as before, but the compiler prints the code that actually gets generated at the position where I call the macro. You can see certain things like use programs or bind vertex array, but since you don't know what my other commands actually do behind the scene, I use another debugging tool that's called rptrace. So I'm running the exact same executable, but I use rptrace to record which OpenGL commands are actually called. So here the triangle again, and now I show with rptrace what's actually shown. Oh, sorry, that was the wrong trace file. Hello triangle dot one dot trace. So here, that's it. So just from a normal rendering, all from the macro call is in a nice debugging group, and these are all commands that are executed. It has a call to use the program. It uses a vertex array object, or binds the vertex array object. It sets vertex buffers, draw arrays because I'm drawing triangles, bind vertex array, so to unbind it again. And that's it. That's all that's called for the rendering command. And the command you see here, glDraw arrays, is actually not always the same. In my case here, drawing with draw arrays is very suitable, but if there's another OpenGL drawing command required because I have some instancing attributes, the other drawing command is generated instead. So in the initial frame, in frame 0, there's also all the code that's required to set up the rendering. Default setup is at this point not interesting, or if you want to see it, here it is. Here are here's the buffer data written to the buffers, and in the shading macro, the program is created, and you can see that the shaders are attached, and everything is done basically to set the things up. This is just run once. To give you more information about it, it runs lazily. So the first time the execution of the program comes to the point where the macro was expanded, there's a variable that checks is the shader already compiled? If no shader is compiled, this complex code is executed, otherwise it just calls the drawing commands. I thought of writing a macro a little bit differently that collects all the instances where I have those macro calls, and then at program start I compile every shader so that at program start I also get every possible problem with the shader compilation stage. But I didn't do it, so that's it. Thank you for listening. Hello again. Now I want to show you a renderer that's a little bit more complex. I show you first how it looks like. So you see a box, you see face normals, because the box consists of 6 sides. Each side has 2 triangles, so 12 faces, therefore 12 face normals. And you see a post-processing step that is supposed to resemble a little bit like how you see water when you look through water, but it's not intended to look realistic. It's just for the it's just an effect so that I use a frame buffer and not an effect to actually have the effect on its own. And as you can see, the post-processing step only affects the cube but not the face normals. So now I'm showing you how I do this. So I start with loading the texture from a file. Very simple so far. I've an array buffer for all the box information. So yeah, this, by the way, is important for interleaved data. So I get an interleaved view on the positions, the normals, and so on. Not important at this point. What's important is this part. Here I have a macro that declares a frame buffer type. This is the name. Here I use the name with a new in front of, so that I create a frame buffer of this type and store it in the variable fb1. The frame buffer has a depth and a color. Depth is a predefined name because every frame buffer needs to have a depth attachment or a depth texture, and then an arbitrary amount of color textures that I can render to. And the color can be any name, and I can also have more targets. For example, I can render to a second color. I'm showing you later. This here is just some shader code that I want to reuse, so I include it. Projection matrices, basic rendering stuff. So this is the interesting part where I use my frame buffer. So write to frame buffer block. Here, block bind frame buffer. This is a call that sets an environment where or better said, where my macro knows what colors I'm actually writing to. So I have frame buffer 1. I have my clear command, so OpenGL knows that I'm calling this while the frame buffer 1 is bound. And that also means that in my shading DSL, when I'm in the fragment shader, that I can only render to the output variable color. So just to give you an impression, when I change the name here from color to, let's say, color XY, then I will get a compilation error at several points. So let me fix them. Here This is called color XY. Here it's also color XY. Color XY. So, okay, now I have shader compilation problems, and here where undefined variable color, because the shader that I generate actually requires me that I write to where is it? Uniform in layout location 0 out vec for color XY. So in the shader I have to use the name color XY, and then it works again. When I want to attach an additional color that I render to, I can also say color, no, not color, just something is new texture 2D window size. So this works. I haven't found a solution to reduce that I have to type window size over and over again, but I will come up for a solution for that eventually. I hope so. And now I can also set something to something. Something equals back for 1, 2, 3, 4. Yay, it works. So no problem, but I'm definitely not using that texture yet. But you get the idea. It's that simple to add a new render target to a frame buffer. So here the block ends from where I render to the frame buffer. So now the rendering to the frame buffer is done, and I can render from the textures that the frame buffer gave me and apply the post-processing step. So this is the post-processing step. Here I have a shader that only has a fragment main. And when I'm only providing the fragment shader, it means that it has the fallback solution that I probably want to render a screen space quad. So this is for rendering the screen space quad, and I need to pass the information from the frame buffer. So you see here uniform texture. I want to use the color XY from my frame buffer 1 and with the name text, and you see here where I'm using it, text, that I can access it very easily. And fragment depth is also set from the texture, otherwise the normals that I render that are not with the post-processing effect on top of them, they would not be hidden from the, or they would not be hidden from the cube. So here's the renderer for the normals. Here are also a few interesting parts, because here I'm using a geometry shader. This is not the perfect solution, but I think it's very usable. I have a vertex main, I have a vertex out as in the other aspects, but after the vertex shader I have a geometry shader, and I can just use the output variables from the vertex shader in the geometry shader. Here I have some additional information for the layout, but here you see a very simple geometry shader. It reads the 3 coordinates from the vertex and creates the normal with the cross product. And then emits 2 vertices, one at the center and one at the center plus the normal. And as you can see here, I'm emitting line strips. So after that there's a fragment shader, but I'm just rendering lines, so all I'm doing in the fragment shader is setting a color. That's it. That's all I need to do for the geometry shader. I can run it again so you can see it. So that's it. Here in the end there's just the main loop for polling events, so that escape quits it, and then there's a frame counter, but that's it. Thank you for listening. Okay, here the last example that I'm showing. Here I won't go into too much detail because this is just a project to show how this library works when you actually want to write a program, and for that I decided to clone yet another Tetris clone. Or not clone the Tetris clone, but cloning Tetris. So the total program is 722 lines long. It has animations, it has 3D graphics, and it has audio. It's not perfectly done, and there's definitely a lot of things that could be improved upon, but it's a working example. So I want to show you how it looks like. I'm hearing the music pretty loud at the moment, but that's the game. It works. So I have sound, I have data in this file. Okay, sound actually comes from somewhere else. I don't own the audio, so I have never included the sound files in the official project. And I'm not using the audio in this video either. But I'm hearing it, and if you have the project and put your own music in the folder of the resources where the sounds are located, they should be loaded. Something that I should mention is here's the input management. Where was what I wanted to mention? Here's an iterator that iterates over all block positions, and it creates a buffer with all positions where I want to render a block on screen each frame. And with these positions I can create the buffer that's then used for instancing. And here is a renderer for instancing. Here it's called render mesh instanced, but it's basically again just calling the macro again, but this time with a little difference. Here a divisor of an attribute is set to 1. That enables not only the attribute but also sets the divisor in the setup phase, and therefore this attribute can be used to do instancing. So everything that needs to be passed to render a mesh instance is a mesh with mesh data where I have indices and vertices. This is a very trivial mesh format. Then I have the object position. This is, as you can see, instant data where I want to render the object. I have an object color, so every object that I render can be rendered in a different color. And that's the instance data, and then an integer for instance data, because these objects, I can ask their size, but that would require a call to OpenGL that can be avoided, so I also pass it as an additional parameter. Yeah, that's it. That's all I wanted to say about the example. Okay, I run it again. Okay, enough of playing. That's it. Thank you for listening.